In this video, we will talk about a second form for the definition of the derivative that involves a limit as x approaches a. So I want to begin by drawing a picture. So I'm going to draw some axes, and then I'm going to draw the shape of a graph. So let's say my graph looks something like this. So I have this graph, and I'm going to mark some point on the graph. Let's say where the x coordinate is a. And let me call this graph y equals f of x. So that means that point, its coordinates are a comma f of a. And my ultimate goal is going to be to get the slope of a tangent line at that point. So what I'm going to do, as we've done before, is I'm going to connect that with a nearby point. I'm going to call this x. Okay, and so the coordinates of this will be x comma f of x. So if we connect that with the point at x equals a, we get a line like this. We get a line like that, and that is a secant line. So now, if we take this point on the graph, this green one, x comma f of x, and if we move it closer and closer to the point where the x coordinate is a, the secant line will become the tangent line. So what I'm going to try to do now is draw a tangent line. The line that I draw has to match how steep the graph is at that point. So that looks like it'll be something like this. It's kind of matching how steep the graph is right there. And that is our tangent line. Okay, so we are going to be setting up an expression for the slope of that tangent line. So our derivative will tell us what the slope of that tangent line is. So we are going to get the derivative of our function, this time when the x coordinate is a. And what we're doing is we're going to find the slope of the secant line, which is f of x minus f of a. That's the change in y over now the change in x, which is x minus a. So that's my slope formula. But we got to take a limit. We are going to be taking the limit as x approaches a. Okay, so I'm going to box this. This is also the definition of the derivative. It's just another form for it. I'm going to call this form 2. So when we compute a derivative of a function using the definition of a derivative, we can use either form. We can use either form, either this new one that we've just learned, where x is approaching a, or the one that we have from before, where h is approaching 0. Unless, of course, we do a problem that specifically asks us to use one form. But if it doesn't specify which form to use, we can use either. So let's look at an example. I'm looking at the function x cubed minus 4x, and I want to compute the derivative using this limit as x approaches a. So we've done this already using the other definition of the derivative, and I want to use it using this form to compare. Okay, so we are going to have our derivative at a. This is the limit as x approaches a of c of x minus c of a over x minus a. And now let's start to plug in. So with the limit as x approaches a, c of x is this function. It's x to the third minus 4x. So that is c of x. And now we got to subtract. We are going to have to subtract all of c of a. So let me put a big old parentheses, so I know how to subtract everything that comes after it. And c of a, I have to plug in the a now for my x to get a cubed minus 4a. So c of a is this right here, and then all over that x minus a on the bottom. Okay, so we need some way to simplify this. The limit as x approaches a. So if I distribute the negative sign, I get x cubed minus 4x, and then minus a cubed plus 4a over x minus a. We notice that on this numerator, we have 4 terms. And we've seen a strategy for that back in our algebra pre-calc review. It's to try grouping. We're going to try to group this. And we've actually seen an example very similar to this before, so we might recognize what grouping is going to do the trick. It happens to be putting the cubes together and the other 2 terms together that are not cubes. So let's rearrange it to put those together. The limit as x approaches a. Let's put x cubed minus a cubed together, and then I'll do the minus 4x plus 4a after that. It'll turn out if you grouped it differently, the two groups would have no common terms, and you'd get stuck, and that would just mean try a different grouping. So we get the limit as x approaches a. So now for my difference of cubes, we will get x minus a times x squared plus xa plus a squared. And now from the second group, I can take out 4 or a negative 4. Negative 4 will be a little bit better because I'm left with then x minus a. And over x minus a, because now I see there's an x minus a here and an x minus a here, common term, so I could factor that out. We get the limit as x approaches a. Let's factor out that common x minus a. Because from the first group, I'll now be left with x squared plus xa plus a squared. And from the second group, I'm left with the minus 4. So this all over x minus a. Now the x minus a's cancel. And from there, let's plug in. If I plug in the a for the x, we get a squared plus a times a plus a squared minus 4. Okay, and this simplifies to 3a squared minus 4. So what we've just figured out is c prime of a is 3a squared minus 4. So it's good kind of stylistic notation because the original variable was in terms of x, to write my derivative in terms of x at the end. So as a final step, let's rewrite it in terms of the original variable. And that just means let's just change that a to an x. So we get c prime of x will equal 3x squared minus 4. Alrighty, so that is our answer. So I want to end this video with some key takeaways about our two forms for the definition of the derivative. So we've done this problem that we just did using both of the forms. So we just did it as x approaches a. Earlier we did it as h approaches 0. In general, if you use the limit form as x approaches a, this typically involves more factoring, but less terms. Whereas if you do use the limit as h approaches 0, here was our work for that problem. Notice that there were a lot more terms because I had to expand stuff, but the factoring was easier because I just factored out an h. So this other form, the first one we learned, this typically involves more expanding and has more terms. In terms of our goals, we've now talked about how we can use the second form for the definition of the derivative, this limit as x approaches a.